So in this particular video, we have a system of three blocks. So one of these blocks is resting on a table, and then two blocks are hanging. The coefficient of kinetic friction here between M3 and the table is 0.18. It's just assuming the strings and the pulleys have no mass. All right. So if you need to pause the video and read part A, B, C, and D to yourself. Other than that, I will go ahead and reference the diagram and show you how to do these different parts. So here's M3 of 4 kilogram that's resting on a rough surface, and the coefficient kinetic friction between the surface here and the M3 block is 0.18. Here are two hanging masses, M2 and M1. M2 is 2 kilogram and M1 is 0.5 kilograms. Okay. Part A asks us to find the kinetic friction force F of K acting on M3. So the only block that experiences friction is M3 because it is resting on a rough surface, and that's indicated by the coefficient of kinetic friction given to us as 0.18. Okay, so let's go ahead and do part A and B on the slide. To do part A and B properly, you should identify your forces given out first. Here, there's a hanging mass M1. If there's a hanging mass, it's going to contribute to the acceleration of the system. M1 here is hanging, so therefore it has to have a weight pointing down. I label that as F of G1, and F of G1 is simply mass 1 times the acceleration due to gravity. But as it's moving down, there is a tension connecting it, and then it's going to slow it down, okay? But I'll go ahead and call this second arrow here that just came up F of G2, because there is a hanging mass. There also has to be an F of G2. Here I just drew F of G1 slightly shorter than F of G1 slightly shorter than F of G2 because F of G2 has more mass. And then I'll go ahead and call the tension and string for this diagram. You can call it whatever subscripts you want, but I will go ahead and call this these two red arrows T1. So I'll call this string my first string. But if you want, you can call it T2. It doesn't really matter. Okay. Here in the green arrow that just came up, I'll call that T2 because that's my second string. So I'm going from bottom to top left. If that's T2, there has to be an equal magnitude and opposite vector as well. So this is T2 acting on M3. So once you have all your forces drawn out, it's easy to do. But you notice here in this particular problem, there is friction on M3. So I will go ahead and label this particular black arrow F of K. F of K in this case is going to point left because the system is going to be pulled to the right. Okay. Other than that, let's go ahead and crack out part A to find the kinetic frictional force F of K. We can just use this particular function. The frictional force is the coefficient times the normal force. But here, the only box that experiences friction is M3, which is resting on the surface. So in order to figure out what F of N is, you should draw the vertical forces for M3. So here, the black arrow that just came up, that is the weight of M3. So the weight of M3 is going to push down on the table. But at the same time, the table is going to push up on the box to keep the acceleration in the vertical direction 0. So in this particular problem for M3, there are only two vectors drawn. One pointing down, one pointing up, but those two have to equal in magnitude. So therefore, this vector that's pointing up, we call that the force exerted by the table onto the box. And that is going to be called our normal force here, okay? So wherever F of N is, I know F of N is equal to the weight of M3 that's pushing down on the table. So I can do a quick substitution. Instead of F of N, I can replace F of N with F of G3. But then we also know F of G3 is just the mass times gravity, the mass M3 times gravity. Okay, so just make sure you pay attention to your masses as you deal with systems of multiple masses. All right, and now we know everything. Mu k is given is 0.18, M3 is 4 kilograms, and then acceleration due to gravity here is 9.8. Excuse me. It says meters per second square. There's a little extra s there. Just ignore that. My apologies. Okay, so that little s should not be there where my cursor is blocking it out. And if you do all your calculator work, you should get a value of 7.06 Newton. But here I've chosen to include the negative sign because according to the diagram, F of K is pointing left, and in part A, it didn't use the word magnitude. So for this motion, F of K is indeed pointing left, and left in this case would be negative. So your answer would be negative 7.06 newtons. All right, that's that. Part B asks us to find the magnitude of the acceleration in the system, which is okay, not too bad. You can convert this whole entire diagram into a horizontal diagram if you like. You don't have to, but in case this gets confusing for you, I encourage you to just open up the system, and then just redraw everything. So here, the purple arrow, that's f of g1. If you open up the system, f of g1 is going to be pointing to the right. And then here are my tensions T1 in red. So pretty much I'm redrawing it, except everything is going to be pointing right and left instead of, up and down, like right and left. I think it just simplifies problems. And then f of g2 is going to point to the right as well. There's T2 in green. And then last but not least, there's f of k in black. Okay. So to find the acceleration in the system, you can totally, if you want to, combine M2 and M1 for this diagram. So you have to know what to combine. You can indeed combine these two hanging blocks into just one big block. So which is what I've done here. So instead of writing M2 and M1, I just combine these two smaller block into one big block. And I'm just going to call it M1 plus M2. You don't have to, but this is something I just like to do. It just helps simplify things. All right. So therefore, I will calculate the weight of this combined block, which is f of g M1 plus M2. So you notice on the right side here, I have M1 plus M2 in parentheses, and then times that by the acceleration due to gravity. Okay. And here's T2. So I just combine the first block just to reduce the amount of arrows that you have to play with. And then last but not least, the kinetic frictional force just gets carried down here. All right, so to find the acceleration in the system, excuse me, I would just use Newton's second law for the system. So it'd be net force of the system equals m total times the acceleration in the system. But if you look at this particular diagram that I've simplified, here is the weight of M1 plus M2 that's going to cause the system to move. And then anytime you do the system, you can ignore the tension that's in the center connecting these blocks, okay? Because they naturally cancel out. There's one pointing right, but there's one pointing left, but they have the same magnitude, so they'll always cancel out. Why they do exist, they don't really matter if you look at the system as a whole, okay? But the only thing you cannot combine is f of k. So really in this particular problem, I just have f of g 1 plus 2 minus f of k, because again, I'm ignoring the tensions in the string here because they naturally cancel out. So here's my work, f of g 1 plus 2. That's going to pull the system to the right. I'm going to subtract that from the block that's sitting on the table, which is f of k due to m3, and then divided by the total mass. So if you plug values in, f of g of the block 1 and block 2, m1 m2 is 2.5 because 2 kilograms plus 0.5 kilogram is 2.5 kilograms. And then times that by g, which is 9.8. And we're going to subtract that from f of k that we calculated in part A. The magnitude of f of k is 7.06 newtons. And here we already introduced our negative sign, suggesting that it does oppose our motion. So the negative sign accounts for the fact that f of k is already negative, okay? So it'd be minus 7.06 Newton divided by the total mass of the system, which is 6.5 kilogram. Here's 4 kilogram plus 2 is 6. 6 plus 0.5 is 6.5. And if you simplify that on your calculator, you should get a value of 2.68 meters per second square. And it says magnitude, so I'm just going to leave the answer as that. All right, let's go ahead and crack out part C and D on the next slide. To do C and D, C asks you to find the magnitude of the tension between M3 and M2. So here's M3, here's M2, here's T2, and here's also T2. You have options here. You can either look at M3 to find T2, or you can look at M2 to find T2. I want to choose the easier route. I want to choose M3 because there's only two forces acting on it. There's T2, which is going to cause M3 to accelerate to the right, but there's F of K acting against the block, and this block is on the table, so there is kinetic frictional force there. You could do M2. I just don't like M2 as much because there are 3 vectors, 1, 2, 3. So I'd rather do M2. Excuse me, I'd rather do M3 because there are only 2 vectors acting on it. So it just reduces the amount of work you have to do. Okay, so therefore, to find the magnitude of T2, I'm going to use M3's perspective, but to do M3 correctly, I would just use T2. T2 is it's what's causing M3 to move to the right. But as it moves to the right, it's going to go against this rough surface, which implies there's an F of K, so I want to subtract that. And here is M3 because I've chosen M3's perspective. Again, you have to be consistent with the mass perspective that you're in. Otherwise, you might plug in the wrong mass and make something easy super complicated and get stuff wrong. All right, so to find T2, I want to move the negative F of K to the right side of the equal sign, which changes to a positive sign. And here I know everything already. Mass 3 is 4 kilograms. Acceleration, which I already found, which is 2.68. And then F of K here, the magnitude of it is 7.06. I do want to remind you that for here, where f of k is you plug in 7.06, not negative, because the negative sign has already been taken care of for you in the first statement, okay? So pay attention to your negative signs as you practice here. All right, if you do that, and you simplify this on your calculator, you should get T2 is equal to 17.78 newtons. And that is our answer. It's just magnitude, so I don't have to include the direction. And then part D wants us to find the magnitude of the tension between M2 and M1. So here's M2 in the middle. Here's M1 on the right side. To do this, I want to choose the perspective of M1. For the same reason, it has the least amount of vectors touching it. Okay, so what is causing M1 to accelerate to the right is its own weight. Its own weight is F of G1, which is simply mass 1 times G. Now, what's acting against it? Well, it's hooked up to a string, so therefore the string is going to slow it down. So these systems to the right here is going to cause M1 to move slower, which makes sense. So therefore, to do this particular problem, part D, I would just set up F of G1, which is the force causing M1 to move to the right, but at the same time T1 is acting against it. So I have F of G1 minus T1, which is equal to M1A. But then to solve for T1, I want to move T1 to the right side, which makes it positive, and I want to move this M1A to the left side, which makes it negative. So this is what it looks like. Okay, so focus on what you're being asked to find. I was asked to find T1 in part D, so I want to use this particular algebra maneuver. I want to solve for T1 first, and then F of G1 is just by definition M1 times G, and then M1 and A just gets carried down. Here in the statement, we notice that we have M1 in both terms, so I can just factor that out. Here, you don't have to, but I'm just factoring out just to show you a little algebra manipulation here in case you're asked to derive an expression or, pick a statement that's true, okay? So here we have M1 in both terms, so we can just factor that out. So it'll be G minus A, so it'll be M1 parentheses, G minus A, close parentheses. Other than that, we know M1 is 0.5, we know that G is 9.8, we plug in again 9.8 here because we take the line of motion to be positive. So be careful with your negative signs. Get comfortable with it and make decisions that make sense. All right, A here is 2.68. Therefore, if you simplify this in your calculator, you just get a value of 3.56 newtons. So that is the magnitude of T1. If you don't like that and you like percentages, as I presented in the videos and during class, you can totally do percentages for any boxes you like. So here's a reminder that you can do percentages if it makes sense in your head. Well, to find T1, I can just do the mass of M1 divided by the total mass of the system. So here in the numerator, I have 0.5 kilogram because that's the mass of just M1 divided by the mass of the system and times it by the net force. Excuse me. The net force here is 17.42. And this value comes from taking the mass total, or the total mass times the acceleration of the system, okay? So if you punch in 6.5 kilograms, which is the total mass, times the acceleration of the system, which is 2.68, you should get 17.42. So the total force on the system is 17.42, but how much of it is going into M1? Well, this much percent, so 0.5 divided by 6.5. And that should give you a value of about 1.34. So there's 17.42 newtons as a total force on the system, and only about 1.34 of that is allocated to M1. Well, once you know net force on M1, you can make a statement that's true. The net force on M1 is simply F of G1, which is this arrow here, subtracted from T1, which is acting against M1. And here you know a bunch of values. We just found the net force on M1 is 1.34 by doing percentages. We know F of G1 is 4.9 because M1 is 0.5. 0.5 times 9.8 is 4.9. So that's where the 4.9 comes from. Minus T1. So here, we're solving for T1. So I want to move T1 to the left side of the equal sign, which makes it positive. But at the same time, I want to move this 1.34 to the right side, combining like terms. So therefore, 4.9 minus 1.34 will give you a value of 3.56. So as you can see, it gives us the same answer as this strategy here. All right, so pick a strategy that works for you the best, or as you practice, do both and just get really comfortable with it. It'll give you an alternative way to check to see if the answer makes sense. All right, other than that, stay nerdy, don't be whack.